In this video, we are going to introduce a very important concept in logic called equivalence. By the end of this video, you'll learn what equivalence is, why it's important, and one way of how we can check two propositions are logically equivalent. And as always, we start with its definition. As always, we will start with its definition. We see two compound propositions denoted by P and Q are logically equivalent, or in short, equivalent, if their truth values always match. And here, we introduce a new notation. These three horizontal bars represent this equivalence relation. So if P and Q are equivalent, we write this way. In the last video, we talked about three concepts based on the truth values of a proposition. If you remember, they are satisfiability, tautology, and contradiction. Now I want to show you these two seemingly irrelevant concepts, equivalence and tautology, are actually related. The first relation is P and Q are equivalent when P, if and only if Q, is a tautology. Why is that? Because we know if P, if and only if Q is a tautology, by definition, it means this proposition is always true. And now if you recall the truth table for this biconditional connective, P, if and only if Q is true when P and Q have the same truth value. And by definition of equivalence, that means P and Q are equivalent. The second one is a proposition P is a tautology if and only if P is equivalent to true. Here I use this letter T represent true. Why is that? First of all, let's look at from the left to right direction. If a proposition P is a tautology, then of course by definition of tautology, we know P is always true. Therefore, we can write it as P is equivalent to true. On the other hand, if we know P is equivalent to true, then we know that P and true always have the same truth value. In other words, P is always true. Then by definition of tautology, we know P is a tautology. Next, let's look at some examples on how can we check two propositions are equivalent. So the top one is the implication we are all familiar by now. A implies B. And for any implication, we could write its corresponding contrapositive, which is not B implies not A. And its converse is B implies A. Next, we're going to see an example to show how to find an implication's contrapositive and converse. So the example of the implication is, if it is raining, then the home team wins. In order to write its contrapositive or converse, we need to be able to identify which one is A, or in other words, the hypothesis, which one is B, or in other words, the conclusion. And since this one is in its standard if-then format, we know A should be it is raining, B should be the home team wins. Then we can just substitute this in its general contrapositive form and the converse form, and we have for the contrapositive, it is if the home team does not win, then it is not raining. And its converse is, if the home team wins, then it is raining. Okay? Now my question for you is, are these three propositions equivalent? Well, you may ask me, how can we check that? To answer that, think about the definition of equivalence. The definition is two propositions are equivalent if their truth values always match. So how do we know that? Here, we're going to use what we learned before to answer that, which is truth table. So I'm going to draw the truth table for all three propositions, and then you can compare row by row to decide whether they are equivalent. Here is the truth table for all three of them. We have two variables, therefore the first we have these two columns. And this one is just the standard implication. This one and this column just shows the truth value of the implication. And for this one, you can quickly check the truth values. For the first row, since B is true and not B is false, therefore you don't need to check the value of not A. Based on the truth table of implication, we know not B implies not A must be true. For the second row, B is false, not B is true. A is true, not A is false. Therefore, you have true implies false. Then the whole implication is false. So that's, you can decide the truth value of this implication for the third and fourth row. And similarly, you can decide the truth value for B implies A in the last column. Now, by looking at this truth table, let's answer the question, are they equivalent? So for these two, the implication and its contrapositive, you can see for every combination of the truth values of A and B, they always have the same truth value. Therefore, these two are logically equivalent. However, for B implies A, you can clearly see that they do not always match. Therefore, we can conclude A implies B and its contrapositive are equivalent. What about another proposition, not A or B? Is this one equivalent to the implication? Let's check together. When A is true, B is true. Not A or B is true because B is true. Therefore, for that row, they match. When A is true, B is false. So not A is false, B is false, false or false, which is false. And you look at this one, it's false as well. Therefore, they still match. For the third row, A is false, then not A is true. Then true or anything is always true. Therefore, you can look at this one, they match. For last row, similarly, not A is true, so true or anything is true, then this one is also true. So they still match. Now you can say the implication and its contrapositive, and this one, they are all equivalent. And it turns out this is one of the equivalence laws we are going to talk about next video. Let's see another example. After this example, you are going to see why equivalence is important in logic or in computer science in general. Let's say you are writing code and you write a piece of if statement. The condition is x greater than 0 or x is less than or equal to 0 and y is greater than 100. So now I want to think about, can we simplify this if condition? By simplify, what I mean is, can you reduce the number of inequalities? You can pause the video and give it some thoughts. All right, let's look at this simplification problem together. In order to simplify that, we need to first represent it using logical notations. So let's use A to represent the first inequality, x greater than 0. And use B to represent y is greater than 100. Some of you may ask, why don't we use another letter to represent x less than or equal to 0? The reason is that middle inequality can be represented using one of the letters we have. That's basically not A, right? So now I directly give you this simplified form, A or B. You have to make sure after the simplification, these two, if conditions are still equivalent, we need to make sure these two propositions are logically equivalent. How do we do that? We can use the truth table as well. So you can quickly check the truth values for these two columns, and clearly you can see they always have the same truth value. Therefore, by definition of equivalence, they are logically equivalent. Therefore, we can simplify this if condition to this one. You can see it is much simpler. Why do we want to simplify our code? The reason is if it's simple, then we can improve the readability. In addition, if the code is simple, especially those conditions are simple, then after you compile your program will run faster. And not just for coding. When you design chips, you know we need to put a lot of gates on a single chip, which is very, very small silicon. Therefore, if you can simplify the logic, in other words, if you can reduce the number of gates you need to implement certain function, then you can definitely reduce the cost, reduce the energy needed for this chip, and you may also improve the efficiency. That's why logical equivalence is very important in computer science.